Good morning, everyone. Thanks to the organisers for persisting and finally getting us here. So I'm going to first talk about some lab experiments, and then I'm going to move on to some theory that was inspired by some of the results from the experiment. The experimental part of my talk is a collaboration with Alessandro Toffoli, Alberto Albarello, who's in the back corner over there, and it's really a complete project. It was published earlier this year in the Journal of Physical Oceanography, and I'll give you the reference at the end of the talk. In contrast, the theory, which is being led by Jordan Pitt, who's up the front here, is all preliminary, so don't believe any of it. The experiment was conducted in the Aalto University ice tank in Finland. It's 40 meters wide, 40 meters long, so it's pretty large. At the far end, what you can see there is the wave maker. At the opposite end, below the camera, is a linear beach. It was filled with water up to 2.8 meters in depth, which all you really need to know is essentially that's going to mean we're operating in deep water conditions. The water was ethanol doped in order to make the model ice. And we grew a model ice cover across the water surface, 3 centimeters thick, and then we got rid of the first 10 meters in from the wave maker. You can see that there. The objective of the experiment was to use waves to break up this ice cover. So you can imagine this could be Pat's fast ice that we're about to break up with waves. Like that. Okay, so I mean, that I think sounds quite simple to do. To my knowledge, it's only been done once before in the lab, and that was by us, by the same team. It was only in a small wave flume, and it was using freshwater ice, so quite different from this. So look, for anyone who doesn't know, model ice is quite difficult to grow. Luckily, I had absolutely nothing to do with it, and it's quite time-consuming. In particular, there's some warming, cooling process that goes on in order to tune the flexural strength. And we wanted the flexural strength so that the equivalent field scale flexural strength is realistic at a scaling factor of just below 30 for us. The thickness is also realistic with that scaling factor. The Young's modulus is an order of magnitude too small. I mean, this is just standard for model ice, and it's really something we have to live with when we're working in the lab with an experiment like this. Here's a schematic of the initial setup of the experiment, which also shows the instrumentation. On the left there, we've got a line of 3 wave gauges in the open water to measure the instant waves. Then below the ice cover, we have got a line of 5 pressure sensors to measure the waves in ice. We've got the camera, the image you saw before, that's pointing down the ice cover, and that's going to monitor the response of the ice cover to the waves. We also had a line of motion sensors on the ice cover, but you can pretty much ignore them because the data didn't prove to be too useful. Right, so actually, this experiment was due to be conducted in 2016, so really I should have been presenting this at the program in 2017, but then it was delayed and delayed. Eventually, it was conducted in 2019. We got 1 model ice cover. We performed 3 tests on that ice cover. And we came in with the philosophy that between the tests, we're going to increase the steepness of the waves. And we want the smallest steepness test to cause no breakup. and the largest steepness test to break up the entire ice cover. I'm now going to attempt to show you a short movie of the intermediate steepness test. It's quite a short movie if it works, but it's actually 10 minutes worth of footage sped up. Okay. So you see the waves coming in from the open water, getting into the ice cover, causing it to bend and flex, and then breaking up the ice cover at the edge. The breaking front propagates deeper into the ice cover, and then over time it slows down, and eventually it pretty much stops. So we call this a partial breakup test. We used unidirectional, irregular incident waves, obeying the Pearson-Moscovitz spectrum, which is illustrated on the right-hand side here. All of the wave fields have the same peak period of 1.6 seconds. That corresponds to a wavelength of 4 meters. And then we increased the significant wave height in each of the tests in order to get the steepness values 0.02, 0.04, and 0.06. So even the steepest wave is not really that steep in terms of ocean waves. Each test lasted 20 minutes so that we built up a pretty large data set in order to perform a statistical analysis on. Now, this sequence of images is trying to convey how we extracted the information about the flows from the camera images. Any questions about this? I'm just going to direct you to Alberto at the back because he's the expert in this. All I really want you to take from this is that we approximated the flows as ellipses, where the minor axes of the ellipses are typically in the direction of the instant waves, meaning that the major axes are in the direction of the wave crests. We also extracted the ice edge and breaking front, both of which we approximated as straight horizontal lines. So now I'm going to show you some results on how the ice edge and the breaking front evolved over the tests. These are the results for the small steepness test. We have time running along the x-axis, distance from the wave maker along the y-axis. The blue is open water, the white is continuous unbroken ice. That hatched region at the top is outside of the camera field of view. So for this small steepness test, there was no breakup, and all you see here are reasonably small oscillations in the location of the ice edge, and they were observed to be mainly due to the instant waves overwashing the ice edge, which either caused it to crumble or just made it very difficult to detect where the ice edge was. And then we move to the intermediate steepness test. So this is the one that I showed you in the new movie a few slides ago. So the instant waves start breaking up the ice cover almost immediately, and the breaking front travels deeper into the ice cover, and after 5 to 10 minutes it starts to slow down. So by the end of the test, only about a quarter of the ice cover is broken. You can also see that the instant waves are pushing back the broken ice. So then switch off the wave maker at the end of that test. The ice starts to relax, and the breaking front, and particularly the ice edge, starts to move back towards the wave maker for the beginning of the final test. And in that test, we have the large steepness waves, and they break up the remainder of the ice cover relatively quickly. So the breaking front goes outside the camera field of view, but the observations during the test were that all of the ice cover was broken by about halfway through. The instant waves are very strongly pushing back the ice edge here as well. So that's a combination of the ice edge drifting back and also the ice being destroyed by the waves. Now, what I'm showing you here are the the mean lengths of the minor and major axes over time during the intermediate steepness tests on the left, large steepness tests on the right. The averages are calculated over a strip of the ice cover from 5 meters from the initial ice edge to 20 meters from it. The minor axes are in blue, the major in red. They're both normalized by the incident wavelength. Be sure to note that the axes scales have a factor of 5 between them, between the minor to major, major being larger, obviously. And what we see on the left-hand side is that both of those lengths are pretty stable during the intermediate steepness tests. The major is about half of the, more like a third of the incident wavelength. And the minor is sort of about a tenth of the incident wavelength. Then we move to the large steepness test, and both of those lengths, they drop over time. I think that is mainly because the waves are pushing back the ice edge so strongly, so they're pushing the smaller flows at the edge into that strip over which we're calculating mean values. At the end, we have that the minor axis is about 5% of the incident wavelength, and the major about 15%. So this slide is going to be for the flow size distribution enthusiasts among you. These are heat maps of the minor and major axes in the intermediate steepness and large steepness tests, top and bottom. The red lines are linear best fits, and really the main finding here is that the aspect ratio is about 1 to 3 in both tests. Then these are the distributions onto which we put some parametric fits, involve some parameter beta. And we noted that the beta value increases from the intermediate to the large steepness tests. For the minor axis, beta is just below 2, and beta is equal to 2 is a special value because it turns that fitted distribution into a Rayleigh distribution, which is the distribution of the incident amplitudes. Now, I'm not claiming any causation to the correlation here because I don't really understand how the physics would work there. But maybe someone out there is smarter and can find some link. Otherwise, it's just a fluke. So now I'm showing you the attenuation coefficient alpha versus frequency, where we've normalized the frequency by the peak frequency of the incident waves. What you're seeing here are the mean values, they're the bullets. The shaded regions are the uncertainty. And then those colored broken lines are benchmarks that I'll talk about in a few moments' time. The nice thing about performing irregular wave tests is that you get results like this over an interval of frequencies around the peak. If you get away from that interval, what you're seeing is to the left and the right is that the uncertainty grows to a point at which you don't really trust the results anymore. But if we just focus around the peaks there, then we get the linear relationship between the attenuation rate and frequency in log-log space, which is more evidence of there being a power law relationship between those two quantities. Those coloured broken lines are power laws for exponents 2, 3, and 4. So those are values that have been found roughly from analysis of field measurements. So they're just there to show that we're ballpark to the field measurements. And then here we have mean wave statistics at each of the pressure sensors beneath the ice. And I should just say that all of the analysis of the waves we're doing directly on the measurements taken by the pressure sensors. We didn't use them to try to infer the surface elevation because that requires an assumption about the dispersion relation, which we don't want to make. At the top, you can see the first moments, which are like the significant wave heights, and I'll just refer to as significant wave heights to be lazy. In the middle, you've got the mean period, and at the bottom is the spectral bandwidth, and all of these are normalized by the equivalent incidence wave values. And qualitatively, we see what we're expecting. The significant wave height decreases over distance. That's attenuation. The mean wave period increases over distance. That's preferential attenuation of the high frequencies. And the spectral bandwidth decreases, and that again is preferential attenuation. But there are interesting differences between the different tests. And I'm just going to focus in on the significant wave height results. So what we see here is that as the ice cover breaks up, the rate of attenuation increases. But we also see that the significant wave height at the first measurement location increases as the ice cover breaks up. I'm going to refer to that as wave transfer. So there's then some sort of cancellation between this increasing wave transfer and increasing attenuation, so that if you were just taking measurements at the deepest location into the ice cover, actually you find that the results aren't that different. However, if you look at all of them, you can see that the evolution are very different between the different tests. So before someone points this out to me at the end, I'll just acknowledge the fact that you have to take some of these results with a bit of a pinch, because the ice edge is moving. It's moving backwards, especially in that large steepness test. So that first measurement location is not always measuring waves in ice, because the portion of the test, it's open water above. Anyway. All right, so John and I got quite motivated by the experimental results, particularly this concept of wave transfer to set up a theoretical model. We took a 2D water domain. That's the blue in the schematic at the top. The light blue is the ice cover. And we took the first 5 kilometers and broke it up into flows of random lengths, but with some mean length L. And we used the L value to simulate the different phases of the breakup that we saw during the experiment. Then beyond the broken flows, on the right-hand side is continuous unbroken ice cover. That goes off to infinity. On the left-hand side, we have open water that goes to negative infinity. We sent in an instant wave from the open water. It's just a regular instant wave for simplicity. It's got an amplitude A inc and a wavelength 63 meters, so that's 10 times 2 times pi. And then we asked, what is the effect of the mean wavelength L on the properties of the waves in that flow-covered region? Now, we included Robinson-Palmer dissipation in the ice cover, so that, in the first instance, we included it so that the wave would have attenuated by the time it reached the continuous ice cover, and our analysis wouldn't have been corrupted by a reflected wave. But I just want you to note at this point that Robinson-Palmer dissipation is a product of some parameter gamma, which we set to some standard value, multiplied by the time derivative of the surface elevation eta. So that's going to be important in about 3 slides' time, if you try and remember that. So we start out with the continuous ice case, no broken flows at all. And this is going back to basically the Fox-Squire papers from 30 years ago, plus some dissipation in the ice cover. At the bottom here, you're seeing a snapshot of the surface elevation for that problem. So this problem involves scattering at the ice edge. That scattering creates some local exponential motions around the interface between the open water and the ice cover. And that dictates the transfer of the wave from the open water to the ice cover. Then when the wave gets into the ice cover, it gets affected by the dissipation, and that causes it to attenuate. And so what we see there, the wave in the ice, is the product of a wave equation plus some decay. And also note that I'm just showing you the first 500 meters of the ice, just to make things a bit clearer. We then move to what I'll call partially broken ice, where the mean flow length is comparable to the wavelength. That means we're in the scattering regime. And there are lots and lots of ice edges, so there are lots and lots of scattering sources here. But I want to make a distinction between the scattering that occurs at the interface between the open water and the ice cover, which is responsible for the transfer of the wave into the ice cover, and then the scattering of the flows caused by the flows once the wave gets into the ice cover. and that scattering adds to the dissipation in causing the waves to attenuate when they're in the ice cover. Now, in this regime, the randomness of the flow lengths is very important. What I really want you to take from this is that the wave field is random. If I change the random realization of the flow lengths, I'm going to change that wave elevation. And so it's not governed by a wave equation. And then we move to fully broken ice, which here means that the flow lengths are much smaller than the wavelengths. Again, we've got scattering at the interface dictating the transfer. We've got the dissipation in the ice causing attenuation. The role of the scattering in terms of the attenuation is less clear, I think. Because we've made the flows so small that they're going to cause negligible scattering. At the same time, we're increasing the number of flows. So perhaps it's not quite clear what's going to happen, but the solution that's been shown indicates what's going on. It's a decaying wave. So it's governed by a wave equation plus decay, just like the continuous ice cover case. It's telling us that we've moved into a deterministic homogenized regime. The randomness of the flow lengths no longer matters here. We haven't actually calculated the wave equation for this homogenized problem yet, but we will. And now I'm showing some results for the theoretical model that are somewhat trying to replicate the results for the experiments in terms of the wave height versus distance. Here we're also showing the results in the open water, that's the dark blue. For the partially broken ice cover in the middle, the shaded region are the bounds over a large number of realizations of the random flow lengths. And then the circles are the mean values. For the fully broken case, actually there's a shaded region there as well, but it's so small it's just collapsed down to a line, and that's just confirming that we reached the homogenized regime. Just for the sake of simplicity, I want to forget about the partially broken case where random scattering is important, and just contrast what's going on between the continuous and fully broken ice cases. So just like with the experiment, we see that as we go from continuous to broken, we're getting greater wave transfer into the ice cover. And the attenuation rate has increased. But let's just think about that attenuation rate and why it might be like that. Well, the ice concentration is the same in both cases. And there's no attenuation due to scattering to complicate matters in either of these two cases. And now here comes the key part. The Robinson-Palmer dissipation that I told you to remember a few slides ago doesn't depend on the properties of the ice cover. So why are we getting different attenuation rates? Well, I'm going to speculate that it's because the wavelength in the ice cover for the fully broken case is considerably less than the wavelength in the ice for the continuous ice case. But the implication of this is that this debate that's been going on in our community for years and years now about whether it's scattering or dissipation that's causing the attenuation is misplaced. If we want to model the sort of situation that we had in the experiment, where we have an initially continuous ice cover that's been broken by waves, and I'm pretty sure as a community we do want to model this, there's a lot of us who are trying to do that, then we definitely need to know about scattering. In particular, we need to know how the scattering changes, how it affects the wave transfer as we go from continuous to broken. We definitely need to know about dissipation. I think what's really important is we try and work out how that dissipation changes when the ice cover breaks up. Okay, Rebecca's standing up, so I must have run out of time. So look, here are my bland conclusions. Here's the reference at the bottom for the experiment. Please go and look at that. But just reflecting on that thing that Danny asked us all to reflect on during our talks. What do you say, Danny? What do we know now that we didn't know in 2017? Is that right? Well, I would say I don't know any more than I did do previously. However, I think that there's convincing evidence that the attenuation rate increases in broken ice versus continuous ice. So that kind of goes against a lot of observations which have said the opposite. And I would speculate that it's because they haven't considered the wave transfer from the open water to the ice cover, and it's that payoff between the two of them that's making it hard to interpret. And what I want to know, I'd really like to know what controls the speed of the break in front. Okay, that's all.
Nice, so thank you very much, Luke. Any questions?
Hi, Vernon. Well, we did this in 2017 already.
A couple of comments. Firstly, a question about the experiment, which is incredibly hard to do. And I really enjoyed your discussion about it. The question I had, I wasn't quite sure about the beach. Did the ice run up on the beach, or have you got open water on the beach? Because you talked about 95% efficiency, but was that not for an open water situation?
Yeah, the efficiency was with no ice in there. So
yeah, so how does the beach work if you have ice?
The waves very rarely get to the beach.
So it's all attenuated before the waves get to the beach?
Pretty much.
Okay, thank you. The other question, well, it was really a statement. You're thinking of a situation where you have continuous ice that's breaking up, which might happen where you've got a fast ice sheet and the waves break it up. But it's not a marginal ice zone situation.
Sure.
The marginal, I mean, if you think about the Antarctic, which is probably our largest marginal ice zone, it forms as pancake ice because the waves are always there, and it never consolidates unless the waves go away. So the comparison is slightly artificial unless you're looking at a very specific situation of fast ice. Would you agree with that?
Yeah, thanks for making that statement. I agree with you. Now, I'd like to say I never made a claim that it was marginal ice zone, although I did put marginal ice zone in the title because I feel like I'm just trying to connect with that group. So my thinking is that most of the models of breakup in the marginal ice zone are very similar to this sort of thing. We almost always start out with a continuous ice cover that we break up. And until we understand that situation, you're shaking your head at me. You know, they're all roughly the same in my mind. And I would say that we need to understand this first before we can move on from that. Okay, that's my opinion. I'm willing to hear others' opinions on this.
Luke, thanks. Just about the your model for your homogenized limit for all the broken up ice. So you were just talking about the real number, like the real part of the wave number, right? Where you said that it changes in the homogenization limit with long wavelength, short scattering. But in your Robinson-Palmer model, you also have this additional viscous dissipation term. That should also have some effective representation, some effective limit. So, so I think it would be interesting to see what you find when you look at the completely homogenized dispersion equation, basically not just for the real part of the wave number, but also for the imaginary part, because that is of course related to the to your attenuation coefficient.
Sure, absolutely, yeah. I mean, I spoke in terms of wave equations here, but yeah, we're thinking in terms of dispersion relations. And it's going to be very important how that comes into it. So what I was trying to get at is that the dispersion relation is going to change the wavelength, and at the same time, it's going to change, you know, what you and I think of as the imaginary part of the wave number, which is causing the attenuation. So these things just come together. But the other point I was trying to make is that there's no explicit dependence of the dissipation on the properties of the ice cover.
Thank you. Thank you for a very interesting presentation. It's very good to see somebody making tests, this kind of control test. I was intrigued by your statement that the wave attenuation or wave damping, if we call it that way, doesn't depend on ice properties. I would think that ice properties influence them quite a lot. And I just said in the model tests you made that when the wavefront propagates into the ice, creating flows, I think, and one of the other drawback of model ice is that the compressive strength is very low also. So I would think that the damping would be quite high in these laboratory tests, because wave ice is very, well, mushy, if we use the word from the previous presentation.
Look, so first off, yeah, I apologize. I should have said this clearly. I am not saying that the Robinson-Palmer dissipation is correct, but a lot of us use it. And I think the fact that it is so simple and it doesn't depend on the properties of the ice cover have brought out this interesting feature of the dependence on whether the ice cover is broken or continuous. So take, you know, all the theory stuff as all other things being equal, and yeah, so some components of the dissipation being like the Robinson-Palmer one, okay, not being dependent on whether the ice cover is explicitly dependent on whether it's broken or continuous. There are going to be other terms in there, terms that just appear because you've gone from continuous to broken. So what was your other point in there? What, did you have another question? No? That one?
There are a couple of questions in the chat. So one question was, how did you set the parameter for the viscosity in your model?
It's a standard one against field measurements. So we didn't do one, I guess I did it 10 years ago or so. A few different people have found that it works.
The question was, how did you set the parameter for the viscosity?
You're responsible for that as well, Vernon. You're just losing your memory.
Next question then. Oh, sorry.
Oh, so it was a dissipation, Robinson-Palmer dissipation parameter.
Parameter for the experiment. I mean, okay, I'm responsible for the dissipation. I don't recall that conversation, but I don't recall what I had for breakfast either. I was intrigued you said the Young's modulus was an order of magnitude lower. Did you mean the scaled Young's modulus?
Yes.
Because it's 3 orders of magnitude lower than what we
Yeah,
would
yeah.
normally assume in the field. Yeah,
With the scaling factor of about 30.
Yeah, yeah.
Sorry if that wasn't clear.
Yeah, and your last question, have you measured reflection by ice edge in the experiment?
Yes. Can't remember values of it on my head. Yes, it's not. It does change a bit between the different tests. So I'd like person to read the paper. Okay, right. Well, he should definitely read the
You
paper.
can put it in the chat. Great. Okay. Well, thanks, Luke. And we'll move on to our next speaker now. So next we have Ivan Sudoku from the Open University.